Tonight, we're going to explore the single most violent thing that can happen in the universe. Not a supernova, not a black hole collision, something far more extreme. A gamma ray burst. In less than a minute, a single gamma ray burst can release more energy than our sun will produce in its entire 10 billion year lifetime. But here's what most people never think about. That energy doesn't just disappear into the void. It does something to the space around it. It shreds atoms. It superheats gas to billions of degrees. It drives shockwaves that travel for light years, reshaping everything they touch. And the most terrifying part is that almost all of that destruction is concentrated into a beam so narrow that if you're standing in its path, nothing can save you. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that might seem unrelated, but will make everything click. You know what an explosion looks like. You've seen fireworks, you've seen footage of volcanic eruptions, maybe you've watched a controlled demolition bring down a building in a cloud of dust and noise. In all of these cases, the energy spreads outward in every direction. It radiates from a central point like ripples on a pond. The blast goes up, down, left, right, forward, backward. It doesn't pick a direction, it just expands. This is how most people imagine cosmic explosions too. A star blows up, energy goes everywhere, space gets a little brighter for a while, and then things settle down. That mental picture is fine for ordinary explosions. It even works reasonably well for supernovae, which are genuinely powerful events where a massive star tears itself apart at the end of its life. A supernova releases an extraordinary amount of energy, roughly the equivalent of what our sun will produce over its entire 10 billion year lifetime, all compressed into a few weeks of brilliance. That's impressive. That's genuinely powerful. But a gamma ray burst is something else entirely. A gamma ray burst doesn't just release energy, it focuses it. It takes a staggering amount of energy, more than a supernova produces, and instead of spraying it evenly in all directions, it concentrates almost all of it into two impossibly narrow beams that shoot out in opposite directions at nearly the speed of light. This distinction between spreading energy everywhere and focusing it into a beam is the single most important thing to understand about gamma ray bursts. It's what makes them the most violent events in the known universe. It's what allows them to outshine entire galaxies containing hundreds of billions of stars for brief moments, and it's what makes their effects on the surrounding space so extreme, so catastrophic, and so different from anything else in astrophysics. To understand how this works, we need to start at the beginning. We need to understand what actually produces a gamma ray burst. And that means we need to talk about how certain stars die. Not all stars die the same way. Small stars like our sun will eventually swell into red giants, shed their outer layers, and leave behind a dense core called a white dwarf. It's a quiet death by cosmic standards. No explosion, no drama, just a slow cooling over trillions of years. But massive stars that are at least 8 times the mass of the sun and often much more, die violently. These stars burn through their nuclear fuel far faster than smaller stars. Our sun has been burning hydrogen for about 4.5 billion years, and will continue for another 5 billion. A star 25 times the mass of the sun might exhaust its fuel in just a few million years. When a massive star runs out of fuel, something catastrophic happens. Throughout its life, the star has been held up by the energy produced in its core. Nuclear fusion generates outward pressure that balances the inward pull of gravity. It's a delicate equilibrium. Gravity pulls inward. Fusion pushes outward. As long as those two forces balance, the star remains stable. But when the fuel runs out, the outward pressure vanishes. And gravity, which has been waiting patiently for millions of years, wins. The core collapses. Not slowly, not gradually. It collapses at a significant fraction of the speed of light. In less than a second, the inner core of the star, a region roughly the size of Earth containing more mass than our entire sun, crushes itself down to a sphere about 12 miles across. 12 miles. That's smaller than a city. All that mass, more than the mass of the sun, compressed into something you could drive across in 15 minutes on a highway. The density is so extreme that a teaspoon of this material would weigh about 6 billion tons on Earth. This is a neutron star. The protons and electrons in the core have been squeezed together so forcefully that they merge into neutrons. The entire core becomes a single enormous atomic nucleus. For most massive stars, this collapse triggers a supernova. The infalling outer layers bounce off the newly formed neutron star and are blasted outward in a tremendous explosion. Energy radiates in all directions. The star briefly shines as bright as an entire galaxy. Heavy elements forged in the explosion are scattered into space, eventually becoming part of new stars, new planets, and potentially new life. This is a supernova. It's powerful, it's important, but it's not a gamma ray burst. A gamma ray burst requires something more extreme. There are two main pathways, and they produce two different types of bursts. Understanding both is crucial because the physics of jet formation is similar in each case, but the circumstances are different. The first pathway involves the most massive stars imaginable. Stars that are roughly 25 to 40 times the mass of the Sun or more, depending on their composition. When one of these stellar giants dies, the core doesn't just collapse into a neutron star. The core is so massive that even the neutron degeneracy pressure, the quantum mechanical force that holds neutron stars up, can't support it. The core continues collapsing past the neutron star stage and forms a black hole. This is called a collapsar. The word comes from collapsed star, and it describes one of the most extreme events in nature. The core of a dying massive star collapses directly into a black hole, while the outer layers of the star are still falling inward. Now, here's where things get extraordinary. The outer layers of the star don't just fall neatly into the black hole. They can't. There's too much material trying to get through too small a space. The infalling matter has angular momentum, which means it's spinning. As it falls inward, it spirals around the newly formed black hole and forms an accretion disk. An accretion disk is essentially a swirling disk of superheated matter spiraling inward toward the black hole, like water spiraling down a drain, but at nearly the speed of light and at temperatures of billions of degrees. This accretion disk is where the magic happens. The physics of what occurs in and around this disk is extraordinarily complex, involving magnetic fields, extreme gravity, relativistic speeds, and quantum effects. But the key outcome is this: the accretion disk and the black hole together act as an engine. An engine that converts gravitational energy and rotational energy into two focused beams of matter and radiation that shoot outward along the rotational axis of the black hole. These are the jets. And they are unlike anything else in nature. The jets are launched along the poles of the black hole, perpendicular to the accretion disk. They're powered by a combination of forces. Strong magnetic fields threading through the accretion disk get wound up and twisted by the rotation of the disk and the black hole itself. These twisted magnetic fields act like a nozzle, channeling energy and matter into tight columns that blast outward at extraordinary speeds. The material in these jets is accelerated to what physicists call ultra-relativistic speeds. We're talking about 99.99% of the speed of light, or faster. At these speeds, the physics of special relativity becomes dominant. Time dilation, length contraction, and relativistic beaming all play critical roles. The jets aren't wide, they're incredibly narrow. A typical gamma-ray burst jet has an opening angle of just a few degrees. Some are as narrow as 1 or 2 degrees. To put this in perspective, if you held your hand at arm's length, the jet would be narrower than your little finger. That's the width of a beam that carries more energy than our sun will ever produce. This narrowness is absolutely critical. If a gamma-ray burst released its energy uniformly in all directions like a supernova, the energy per unit area at any given distance would be spread thin across an entire sphere. But because the energy is concentrated into a jet covering maybe 1% or less of the sky as seen from the source, the energy per unit area within that jet is hundreds or even thousands of times more intense than it would be if the same total energy were spread evenly. Think of it this way. Imagine you have a garden hose with a spray nozzle. If you set the nozzle to a wide mist, the water spreads out and covers a large area, but each spot gets only a gentle sprinkle. Now tighten the nozzle to a narrow stream. The total amount of water coming out of the hose hasn't changed, but the force hitting any point in the stream's path is enormously greater. That's essentially what a gamma-ray burst jet does with energy. Same total output, but focused into an impossibly tight beam, making the intensity within that beam catastrophically powerful. Now, there's a subtlety here that most popular descriptions miss. The jet doesn't just magically appear in open space, it has to fight its way out of the star. Remember, this is happening inside a massive star. The core has collapsed into a black hole, the accretion disk has formed, and the jets have launched. But the outer layers of the star are still there. Thousands of miles of stellar material, mostly hydrogen and helium, surround the core. The jet has to bore through all of that material to escape. This process takes time, usually somewhere between 5 and 30 seconds, depending on the size of the star. The jet essentially drills a channel through the star's interior, heating and pushing aside the stellar material in its path. As it does so, it forms a structure called a cocoon. This is a hot, pressurized sheath of material surrounding the jet channel. The cocoon plays an important role in the overall explosion, which we'll return to later. When the jet finally punches through the surface of the star and emerges into space, the gamma-ray burst begins. The burst itself is the moment when the jet breaks free and its radiation reaches the outside universe. The whole process from the core collapse to jet emergence can take less than a minute, but during that minute, the jet has drilled through an entire star and emerged carrying an almost incomprehensible amount of energy. This is the mechanism behind long gamma-ray bursts. They're called long because the burst of gamma rays typically lasts more than 2 seconds, usually between 10 seconds and several minutes, sometimes even longer. The duration reflects how long the central engine, the accretion disk feeding the black hole, remains active, As long as stellar material continues to fall into the disk, the jets keep firing. But there's another type of gamma ray burst. Short gamma ray bursts. These last less than 2 seconds, sometimes only a fraction of a second, and they come from a completely different source. Short gamma ray bursts are produced by the merger of two neutron stars, or in some cases, a neutron star merging with a black hole. Neutron stars are the ultra-dense remnants of supernovae, objects containing more mass than the Sun packed into a sphere about 12 miles across. Sometimes, two neutron stars end up in orbit around each other. This can happen when two massive stars in a binary system both die as supernovae, each leaving behind a neutron star. If the binary system survives both explosions, the two neutron stars continue orbiting each other. But here's the thing. The orbit isn't stable forever. The two neutron stars lose energy by emitting gravitational waves. These are ripples in space-time predicted by Einstein's general theory of relativity and directly detected for the first time in 2015 by the LIGO experiment. As the neutron stars emit gravitational waves, they lose orbital energy. They spiral closer and closer together. This process is slow at first. Two neutron stars might orbit each other for hundreds of millions of years, gradually losing energy and spiraling inward. But as they get closer, the energy loss accelerates. The spiral speeds up. In the final seconds, the two neutron stars are whipping around each other hundreds of times per second, approaching the speed of light. The gravitational waves become intense. Space-time itself is shaking, and then they collide. Two objects, each more massive than the Sun, each smaller than a city, smash into each other at a significant fraction of the speed of light. The collision is violent beyond description. In the first milliseconds, tidal forces rip material from both neutron stars. Some of this material is flung outward. The rest forms a rapidly spinning disk of ultra-dense matter around the merged object, which is either a more massive neutron star or a black hole depending on the total mass involved. Just like in the collapsar scenario, this accretion disk and central object launch jets, relativistic jets that blast outward along the rotational axis. These jets are shorter lived because the accretion disk is smaller and drains faster. The central engine operates for only a fraction of a second to a couple of seconds. But during that brief moment, it produces an enormous burst of gamma rays. In 2017, astronomers witnessed something unprecedented. They detected gravitational waves from a neutron star merger, an event called GW170817, and simultaneously detected a short gamma ray burst from the same source. This was the first direct confirmation that short gamma ray bursts come from neutron star mergers. It was also the first time humans had ever observed the same cosmic event through both gravitational waves and electromagnetic radiation. The discovery confirmed decades of theoretical predictions and opened a new era in astronomy. So, to summarize the two pathways, long gamma ray bursts come from the collapse of very massive stars, whose cores form black holes. Short gamma ray bursts come from the merger of two neutron stars, or a neutron star and a black hole. In both cases, the key mechanism is the same: a rapidly spinning accretion disk around a compact object, either a newly formed black hole or a hypermassive neutron star, launches ultra-relativistic jets along the rotational axis. Now, let's talk about the energy involved, because the numbers are genuinely staggering. A typical long gamma ray burst releases somewhere in the neighborhood of 10 to the power of 44 joules of energy in the form of gamma rays alone. That's a 1 followed by 44 zeros. This number is almost meaningless in isolation. So, let's put it in context. Our sun produces about 3.8 times 10 to the power of 26 joules of energy every second. That's its luminosity, the total power output. If you add up all the energy the sun will produce over its entire lifetime of roughly 10 billion years, you get roughly 10 to the power of 44 joules. A single long gamma ray burst releases energy comparable to everything the sun will produce in its entire life. But it does so in a matter of seconds, not billions of years. Seconds. During those few seconds, a gamma ray burst can outshine the entire observable output of every star in its host galaxy combined. For a brief moment, this single dying star or merging pair of neutron stars produces more light than hundreds of billions of other stars put together. But wait, remember the jet? That energy isn't being radiated equally in all directions. It's concentrated into a narrow beam. If you happen to be looking down the barrel of that beam, the apparent brightness is even more extreme. Because of an effect called relativistic beaming, the radiation from a jet moving toward you at nearly the speed of light appears enormously amplified. The photons are boosted in energy and compressed in time. An observer in the path of the jet sees something far brighter and more energetic than the total energy would suggest if it were spread evenly. This is why gamma ray bursts were so confusing when they were first detected. In the 1960s, American military satellites called Vela satellites, which were designed to monitor for secret nuclear weapons tests in space, started detecting mysterious flashes of gamma radiation coming from deep space. These flashes didn't match any known source. They weren't coming from the sun or from Earth or from any nuclear test. They were coming from random directions in the sky, appearing without warning and vanishing within seconds or minutes. For decades, astronomers debated what these could be. Were they relatively nearby events in our own galaxy? Or were they incredibly distant and therefore incredibly powerful? The debate was finally settled in the late 1990s when astronomers managed to identify the afterglows of gamma ray bursts. These afterglows, which we'll explore in detail later, allowed astronomers to measure the distances to the bursts. And the distances were cosmological. Gamma ray bursts were coming from galaxies billions of light years away. That meant the energy required to produce the observed brightness was almost unthinkable. For a brief period, some astronomers thought gamma ray bursts must be releasing energy equivalent to converting the entire mass of a star into pure energy, according to Einstein's equation E equals mc squared. But then the jet model was developed. Astronomers realized that if the energy wasn't being emitted in all directions, but instead was focused into a narrow beam, the total energy required was much less. Still enormous, still more than a supernova, but not quite as extreme as the initial estimates. The jet model resolved the energy crisis and explained why gamma ray bursts had the properties they did. This brings us to a crucial point. Gamma ray bursts are not the most energetic events in the universe in terms of total energy released. A supernova actually releases more total energy if you count all forms, including neutrinos, which carry away about 99% of a supernova's energy. The total energy of a core collapse supernova, including neutrinos, is about 3 times 10 to the power of 46 joules. That's larger than the total energy of a gamma ray burst. But here's the difference. The supernova's energy goes in all directions and mostly in the form of neutrinos, which barely interact with anything. The gamma ray burst concentrates its energy into an electromagnetic beam, photons, gamma ray photons, and these photons interact powerfully with matter. They ionize atoms, they strip electrons from nuclei, they heat gas to extraordinary temperatures, they push matter around with radiation pressure. The gamma ray burst energy is delivered in the most destructive possible form, as focused electromagnetic radiation moving at the speed of light. This is the fundamental distinction between a gamma ray burst and any other cosmic explosion. It's not just about how much energy is released, it's about how that energy is delivered. A supernova is like a bomb going off in a room. Energy goes everywhere. Everything nearby gets damaged, but the energy spreads thin with distance. A gamma ray burst is like a laser. The energy goes in one direction, and in that direction, the intensity is devastating at distances that would be completely safe from a supernova. Let me give you one more comparison to drive this home. Imagine two explosions, each releasing exactly the same total amount of energy. The first explosion is a bomb. It detonates and sends its energy uniformly in all directions. At a distance of 1 mile, the energy is spread across a sphere with a surface area of about 12.5 square miles. At 10 miles, the energy is spread across a sphere with an area of about 1,257 square miles. The energy per square mile has dropped by a factor of 100. Now imagine the second explosion focuses all its energy into a beam that covers just 1% of the sky. At 1 mile, instead of spreading across 12.5 square miles, the energy hits an area of about 1/8 of a square mile. That same total energy is now concentrated into an area roughly 100 times smaller. The intensity is 100 times greater. At 10 miles, the focus beam still covers only about 12.5 square miles. The same area the unfocused explosion covered at 1 mile. The intensity drops with distance, but at every distance, the beam delivers roughly 100 times more energy per unit area than the spherical explosion. This is what a gamma ray burst does, except the focusing factor isn't 100. It's more like 1,000 or even 10,000. The jet covers a tiny fraction of the sky, and within that fraction, the energy per unit area is thousands of times more intense than if the same energy were radiated uniformly. This is why a gamma ray burst can be dangerous at distances of thousands of light years, while a supernova is only dangerous within tens of light years. Same rough energy scale, vastly different delivery mechanism. The jet is what makes a gamma ray burst uniquely destructive. Without the jet, it would just be an unusually energetic supernova. With the jet, it becomes something entirely different. A focused beam of destruction that can reach across a galaxy and reshape everything in its path. And that's exactly what we're going to explore next. What that beam actually does when it hits something. What happens to gas, to dust, to atoms, to entire star systems when they find themselves in the path of a relativistic jet carrying the energy of 10 billion suns compressed into a beam narrower than your finger held at arm's length. The answer involves physics pushed to its absolute extremes, temperatures measured in billions of degrees, shockwaves moving at nearly the speed of light, radiation so intense it doesn't just heat matter, it tears atoms apart and rewrites the chemistry of everything it touches for light years in every direction. The engine has fired. The jets have launched. Now let's follow them outward and see what they do to the universe around them. The jet has punched through the dying star and broken free into open space. It's moving at 99.99% of the speed of light. It's carrying energy equivalent to what 10 billion suns produce, compressed into a beam only a few degrees wide. And now it slams into the universe around it. What happens next is some of the most extreme physics that exists anywhere in nature. But before we follow the jet into interstellar space, we need to understand what happens inside the star itself. Because the jet doesn't just appear outside the star, it's born deep in the core, right next to the newly formed black hole and its accretion disk. And from the moment it launches, it's fighting. It's fighting against the weight of an entire star pressing down on it. Picture the situation. The core of the star has just collapsed. A black hole has formed. The accretion disk is swirling around it at nearly the speed of light. And now 2 jets erupt from the poles of the black hole, blasting upward and downward through the star's interior. But the star is enormous. A massive star that produces a gamma ray burst might have a radius of several million miles. The jets have to cross that entire distance, boring through layer after layer of stellar material. Hydrogen, helium, carbon, oxygen, all the elements the star fused during its lifetime, stacked in concentric shells like the layers of an onion. Each layer is dense, each layer resists the jet, and the jet has to punch through all of them. This process is violent and messy. The jet doesn't cut through the star like a knife through butter. It's more like a fire hose blasting through a wall of packed sand. The jet pushes stellar material aside, heating it to extraordinary temperatures as it goes. The material that gets pushed sideways doesn't just disappear. It forms the cocoon we mentioned earlier. But now we can see what it actually does. As the jet drills deeper, the cocoon grows larger and hotter, inflating like a balloon inside the star and pressing outward against the surrounding stellar layers. The cocoon plays an important role. It actually helps the jet. As the cocoon inflates, it pushes stellar material away from the jet's path, clearing a channel that makes it easier for the jet to advance. At the same time, the cocoon confines the jet, preventing it from spreading out too much. The jet and the cocoon work together. The jet providing the energy, the cocoon shaping the path. This interaction is incredibly complex. Computer simulations of jet propagation through massive stars require some of the most powerful supercomputers in the world. And even then, they can only capture the broad strokes of what's happening. The actual physics involves turbulence, magnetic field interactions, and relativistic fluid dynamics that push the limits of our mathematical models. The jet takes somewhere between 5 and 30 seconds to cross the star. That might not sound like much, but remember, the jet is moving at nearly the speed of light. The fact that it takes seconds to cross the star tells you something about the resistance it faces. The stellar material is dense enough to slow even a relativistic jet. Some jets don't make it. If the star is too large or the jet too weak, the jet can stall inside the star. It dumps all its energy into the stellar interior without ever breaking through. When this happens, you don't get a gamma ray burst. You might get an unusually energetic supernova, sometimes called a failed gamma ray burst, but the jet never escapes. But when the jet is powerful enough and the star isn't too large, the jet punches through. It reaches the surface, and that's the moment the gamma ray burst truly begins. The instant the jet breaks free from the stellar surface, it's suddenly in a very different environment. Inside the star, the jet was fighting through dense material. Outside the star, there's comparatively nothing. The interstellar medium, the gas and dust that fills the space between stars is incredibly thin. In our region of the Milky Way, the average density of the interstellar medium is about 1 atom per cubic centimeter. Compare that to the air you're breathing right now, which contains about 25 billion trillion molecules per cubic centimeter. The interstellar medium is essentially a vacuum by any standard you'd recognize in daily life. So the jet goes from pushing through dense stellar material to suddenly racing through nearly empty space. It accelerates, it spreads slightly, and it starts interacting with whatever tenuous material lies in its path. This is where the real destruction begins. The first thing the jet encounters is the immediate circumstellar environment. This is the material surrounding the star, gas and dust, that was expelled by the star during its lifetime. Massive stars that produce gamma-ray bursts are often Wolf-Rayet stars, extremely hot and luminous stars that shed enormous amounts of material through powerful, stellar winds. Over the final stages of its life, a Wolf-Rayet star might lose several solar masses worth of material, blowing it outward into the surrounding space at speeds of a few thousand kilometers per second. This creates a bubble of relatively dense gas surrounding the star, extending outward for a few light years. When the jet hits this circumstellar material, something extraordinary happens. The jet is moving at 99.99% of the speed of light. The circumstellar gas is moving at maybe 1 or 2,000 kilometers per second at most. From the jet's perspective, the gas is essentially stationary. The collision between the ultra-relativistic jet and this nearly stationary gas produces a shockwave. But this isn't an ordinary shockwave, like the kind produced by a supersonic airplane or an explosion on Earth. This is a relativistic shock. A shockwave moving at a significant fraction of the speed of light through gas that has no chance of getting out of the way. In a relativistic shock, the physics becomes extreme. The gas ahead of the shock has no warning. Information in a gas travels at the speed of sound, which in the interstellar medium is roughly 10 kilometers per second. The shock is approaching at nearly 300,000 kilometers per second. The gas literally cannot know the shock is coming until it has already arrived. There's no pressure wave running ahead saying something bad is approaching. The shock just arrives instantaneously, and everything changes. When the shock front passes through gas, it compresses it enormously. In an ordinary shock, gas might be compressed by a factor of 4. In a relativistic shock, the compression factor can be much larger, potentially by factors of hundreds or thousands. The gas goes from being thin and cold to being incredibly dense and extraordinarily hot in a fraction of a second. The temperature behind a relativistic shock from a gamma-ray burst can reach billions of degrees. Not millions, billions. To put that in context, the core of our sun, where nuclear fusion occurs, has a temperature of about 15 million degrees. The gas behind a gamma-ray burst shockwave can be hundreds of times hotter than the core of the sun. At these temperatures, matter behaves in ways we never encounter on Earth. Atoms don't exist. At billions of degrees, atoms are completely ionized. Every electron is stripped from every nucleus. You have a plasma of bare atomic nuclei and free electrons moving at nearly the speed of light. And at these energies, the electrons emit radiation. Lots of radiation. There are two main processes producing the radiation we observe from gamma-ray bursts. The first is synchrotron radiation. When charged particles, especially electrons, spiral around magnetic field lines at nearly the speed of light. They emit electromagnetic radiation. In the powerful magnetic fields generated by the shock, the electrons spiral rapidly and emit radiation across a broad spectrum, from radio waves through visible light and X-rays all the way up to gamma rays. This synchrotron radiation is responsible for much of the observed emission from gamma ray bursts and their afterglows. The second process is inverse Compton scattering. In normal Compton scattering, a high-energy photon hits an electron and transfers some of its energy to the electron, losing energy in the process. Inverse Compton scattering is the opposite. An ultra-relativistic electron collides with a low-energy photon and boosts that photon to much higher energies. In the environment of a gamma-ray burst, relativistic electrons can boost ordinary photons into the gamma-ray range, producing some of the highest energy photons observed from these events. Together, these processes convert the kinetic energy of the jet into electromagnetic radiation across the entire spectrum. The jet is essentially a machine for converting the gravitational and rotational energy of a collapsing star or merging neutron stars into light. Incredibly intense, incredibly energetic light. Now, let's talk about what this radiation does to matter in its path, because this is where gamma-ray bursts become truly terrifying. Gamma-ray photons are the most energetic form of electromagnetic radiation. A single gamma-ray photon from a gamma-ray burst can carry millions or even billions of times more energy than a photon of visible light. When these photons encounter matter, they interact violently. The first thing gamma rays do is ionize atoms. Ionization is the process of stripping electrons from atoms. When a gamma ray photon hits an atom, it doesn't just knock off one electron. A single high-energy gamma-ray photon can strip an atom completely bare, removing all of its electrons in a cascade of interactions. In the path of a gamma-ray burst, every atom for enormous distances gets ionized. Not partially ionized, completely ionized. Every electron removed. Every atom reduced to a naked nucleus surrounded by a sea of free electrons. But that's just the beginning. If the gamma rays are energetic enough, they can do something even more extreme. They can break apart atomic nuclei themselves. This process is called photodisintegration. When a gamma ray photon with sufficient energy strikes an atomic nucleus, it can knock out protons or neutrons, breaking the nucleus into smaller pieces. Elements that took millions of years to form through nuclear fusion inside stars are shattered in an instant. Iron nuclei are broken back down into helium and individual protons and neutrons. The gamma rays are literally unmaking matter, reversing the nuclear processes that built these atoms in the first place. This doesn't happen everywhere. Photodisintegration requires extremely energetic photons and occurs primarily close to the source where the gamma ray flux is most intense. But within that zone, the destruction is total. Matter isn't just heated or ionized, it's dismantled at the nuclear level. At slightly greater distances, where the gamma rays are still intense but not quite intense enough for photodisintegration, they still wreak havoc. Gamma rays passing through molecular gas break every molecular bond they encounter. Molecular hydrogen, water vapor, carbon monoxide, all the molecules that exist in interstellar space are shattered into individual atoms. Those atoms are then ionized. The result is a region of space where all molecular chemistry has been erased. Every molecule destroyed. Every atom stripped of its electrons. The chemistry that existed in that region of space before the burst, chemistry that might have taken millions of years to develop, is wiped out in seconds. And the effects extend much farther than most people realize. Consider the inverse square law. The intensity of radiation decreases with the square of the distance from the source. If you double the distance, the intensity drops to 1/4. If you increase the distance by 10, the intensity drops to 1/100th. This means that at large distances, the radiation becomes weaker. But a gamma ray burst starts with such extraordinary intensity that even after the inverse square law has dramatically reduced it, the radiation is still powerful enough to cause significant effects at distances measured in light years. Within a few light years of a gamma ray burst, the radiation is so intense that it would vaporize essentially anything. Dust grains, which are tiny particles of rock and ice floating in interstellar space, would be sublimated, not melted, sublimated, converted directly from solid to gas, or more accurately, from solid to plasma. The gamma rays deliver so much energy so quickly that the dust grains don't have time to melt. They go straight from solid to ionized gas. This has interesting consequences. Interstellar dust plays an important role in blocking light. It's why parts of the Milky Way appear dark when you look at the night sky. Dense clouds of dust block the light from stars behind them. But a gamma ray burst in the vicinity of a dust cloud would destroy the dust. It would create a tunnel of cleared space, a corridor through which radiation can pass freely. This means that the gamma ray burst's effects can propagate even farther than you might expect, because the burst destroys the very material that might otherwise shield more distant regions. Now, let's talk about the shockwave itself, because the electromagnetic radiation is only part of the story. The jet is also a physical object. It's a stream of matter and energy moving at nearly the speed of light. When this stream slams into surrounding gas, it doesn't just produce radiation. It produces a physical shock front that expands outward, sweeping up gas and accelerating it to tremendous speeds. The shock front associated with a gamma ray burst jet is one of the most powerful physical processes in the universe. It moves outward at relativistic speeds, initially at close to the speed of light and gradually slowing as it sweeps up more and more material. As the shock front expands, it compresses and heats the gas it encounters. This creates a shell of hot, dense, shocked gas that expands outward like a bubble. But this isn't a symmetric bubble. Remember, the jet is narrow. The shock front is strongest along the jet axis, where the jet's energy is concentrated. Off to the sides, the shock is weaker. The result is an elongated structure, stronger along the beam direction and weaker perpendicular to it. If you could see it from the side, it would look something like a football or a cigar extended along the jet axis. Within this shock front, particles are accelerated to incredible energies. The shock acts as a natural particle accelerator, bouncing charged particles back and forth across the shock boundary. Each time a particle crosses the shock, it gains energy. After many crossings, particles can reach energies far higher than anything achieved in human-made particle accelerators. These ultra-high energy particles, called cosmic rays, are flung outward into space. Some of the most energetic cosmic rays detected on Earth may have originated in gamma-ray burst shockwaves. The magnetic fields in the shock region are also amplified enormously. Before the shock arrives, the interstellar medium has a weak magnetic field, typically a few microgauss. That's about 1/1,000,000th of the strength of a refrigerator magnet. But the shock compresses and amplifies these fields by factors of thousands or more. Behind the shock front, the magnetic field can reach milligauss or even Gauss levels. These amplified magnetic fields play a crucial role in producing synchrotron radiation, which is the primary emission mechanism for gamma-ray burst afterglows. Let me now walk you through what happens step by step if you were somehow watching a gamma-ray burst jet from the side, not in its path, but off to the side where you could see the whole event unfold. You wouldn't see it in real time, of course. The events happen at nearly the speed of light and span light years, but if you could watch it in time-lapse, here's what you'd see. First, the jet emerges from the dying star. It's blindingly bright in gamma rays, a narrow beam of radiation punching outward into space. The beam is so narrow that from the side, you'd see it as a thin pencil of light, like a laser beam cutting through darkness. Almost immediately, the jet begins interacting with the circumstellar medium. You'd see a bright spot at the tip of the jet where the shock front is forming. This spot is where the jet material is slamming into surrounding gas, producing intense radiation. Behind the shock front, you'd see a trail of hot, glowing gas. As the jet pushes outward, the shock front advances into the interstellar medium. The bright spot at the tip moves forward, leaving behind an expanding column of shocked, glowing gas. The jet itself continues to pour energy into this structure, feeding the shock front and keeping it powered. Over hours and days, the jet begins to slow. Even though it starts at 99.99% of the speed of light, the process of sweeping up interstellar gas gradually decelerates it. The more gas it sweeps up, the slower it gets. As the jet slows, the shock front evolves. It goes from being a narrow, relativistic shock to a broader, slower shock. The emission shifts from gamma rays to X-rays, then to ultraviolet, then to visible light, then to infrared, and finally to radio waves. This gradual dimming across the electromagnetic spectrum is what astronomers call the afterglow. The afterglow is essentially the dying gasp of the shock front as it decelerates and the shocked gas cools. But here's what's critical to understand about directionality. Everything I've just described, the intense gamma radiation, the relativistic shock, the ionization and photodisintegration of matter, all of it is concentrated along the jet axis. If you're standing directly in the path of the jet, you experience the full force of the burst. The radiation hits you head on. The shock wave slams into you at nearly the speed of light. The energy delivered per unit area is at its absolute maximum. But if you're standing off to the side, perpendicular to the jet axis, the experience is completely different. The jet passes by without directly hitting you. You still see some radiation because the shock front does expand sideways to some degree, and the cocoon I mentioned earlier does produce some emission in all directions. But the energy you receive is orders of magnitude less than what something in the jet's path would experience. This directionality is one of the most important features of gamma-ray bursts. A gamma-ray burst is not an equal opportunity destroyer. It's a directed weapon. Something at a distance of 50 light years directly in the jet's path might be catastrophically affected, while something at the same distance but 90 degrees off axis might barely notice anything unusual. Let me put some numbers on this. The isotropic equivalent energy of a gamma-ray burst, that is, the energy it would need to be releasing if it were radiating equally in all directions to produce the observed brightness, can be as high as 10 to the power of 47 joules for the most powerful events. But because the energy is concentrated into a jet covering maybe 1,000th of the sky, the actual total energy is closer to 10 to the power of 44 joules. Now, consider an observer at a distance of 100 light years from the burst. If that observer is directly in the jet's path, they receive the full concentrated energy of the beam. The energy flux, the energy per unit area per unit time, is about 1,000 times higher than what they'd receive if the same total energy was spread evenly in all directions. But if that observer is 90 degrees off axis, they receive only the relatively modest emission from the cocoon and the sideways expansion of the shock. The difference in energy received can be a factor of 10,000 or more. This is why the effects of gamma-ray bursts depend so critically on geometry. Where you are relative to the jet axis matters far more than how far away you are, at least within a certain range of distances. A planet 1,000 light-years away in the jet's path might suffer catastrophic atmospheric damage. A planet 50 light-years away but off to the side might experience nothing more than a brief, faint flash of light, indistinguishable from background noise. To visualize this another way, think of a lighthouse. A lighthouse has a powerful beam that sweeps across the horizon. If you're a ship directly in the beam's path, the light is blinding. But if you're standing next to the lighthouse, you barely notice the beam passing overhead. The total energy output of the lighthouse is the same, regardless of where you're standing. But the energy delivered to your eyes depends entirely on whether you're in the beam's path or not. A gamma-ray burst is like a cosmic lighthouse from hell, except the beam doesn't sweep. It fires once in a fixed direction, and anything in that direction for thousands of light years pays the price. Now, there's one more crucial aspect of how the jet interacts with its environment that we need to cover. Relativistic beaming. This is a consequence of special relativity that dramatically affects how gamma-ray bursts appear to distant observers. When something emitting light is moving toward you at close to the speed of light, the light it emits is concentrated into a narrow cone in the forward direction. This is called relativistic beaming. It's a fundamental prediction of Einstein's theory, and it has been confirmed by countless observations of astrophysical jets. The effect works like this. Imagine a flashlight mounted on a spacecraft. If the spacecraft is stationary, the flashlight beam spreads out normally. But if the spacecraft is moving toward you at 99% of the speed of light, the beam appears dramatically brighter and more concentrated in the forward direction. Photons that would have been emitted sideways are instead beamed forward. The result is that an observer in the forward direction sees a much brighter source than they would if the source was stationary. For a gamma-ray burst jet moving at 99.99% of the speed of light, the beaming effect is extreme. The radiation is compressed into a cone with an opening angle of roughly 1 over the Lorentz factor, which for these speeds is about 1/10 of a degree or less. This beaming effect is what finally resolved the energy crisis we talked about earlier. The apparently impossible energy requirements made sense once astronomers accounted for relativistic beaming on top of the jet's geometric focusing. The two effects compound each other, making the burst appear far more luminous to an observer in the beam's path than the total energy alone would suggest. Relativistic beaming also means that we only detect gamma-ray bursts when the jet is aimed roughly toward us. If the jet is pointed away from us, or even significantly off to the side, we don't see the burst. The gamma rays miss us entirely. This implies that for every gamma ray burst we detect, There are many more that we don't see because their jets are pointed in other directions. Estimates suggest that for every gamma ray burst we observe, somewhere between 100 and 1,000 go undetected because their jets aren't aimed our way. The true rate of gamma ray bursts in the universe is much higher than the observed rate. This has implications for how often material in any given galaxy experiences the effects of a gamma ray burst jet. Even if bursts are relatively rare when seen from Earth, the actual frequency of jets tearing through galaxies is much higher. The universe is full of these events. We just don't see most of them because we're not in the firing line. Let me bring this all together. The jet from a gamma ray burst is not just energy traveling through space. It's a physical process that actively transforms everything it encounters. It ionizes atoms. It breaks apart molecules. It destroys dust grains. It photodisintegrates atomic nuclei close to the source. It drives shock waves that compress and heat gas to billions of degrees. It accelerates particles to energies far beyond what any human-made accelerator can achieve. It amplifies magnetic fields by factors of thousands. And it does all of this along a narrow corridor that can extend for light years or even tens of light years before the jet finally decelerates enough to lose its coherent structure. Along that corridor, space has fundamentally changed. Before the burst, there was cold interstellar gas, perhaps with some dust and molecules. After the burst, there is a channel of superheated, fully ionized plasma threaded with amplified magnetic fields and permeated by ultra-high energy cosmic rays. The chemistry that existed before the burst has been completely erased. The physical conditions have been transformed from cold and quiet to extreme and violent. And this transformation happened in seconds, not millions of years, not thousands, seconds. The region directly in the jet's path has been essentially sterilized, not in the biological sense, though that too, as we'll explore later, but in the physical sense. The matter has been processed through the most extreme conditions the universe can produce outside of a black hole's event horizon. It has been heated to temperatures that exceed the cores of the most massive stars. It has been compressed to densities far exceeding normal interstellar conditions. It has been bathed in radiation at intensities that defy everyday comprehension. And all of this happened because a star died, or two neutron stars merged, and the resulting collapse focused energy into a beam rather than letting it radiate freely. The jet is what makes a gamma ray burst different from any other cosmic explosion. Without the jet, there would still be a powerful event, a supernova or a kilonova. But with the jet, the event becomes something quantitatively different. A directed onslaught of energy that reshapes its environment along a narrow axis while leaving the rest of the surrounding space relatively untouched. The jet has now done its initial damage. It has drilled through the star. It has blasted through the circumstellar medium. It has driven a relativistic shock into the interstellar gas. It has ionized, dissociated, and vaporized everything in its path for light years. But the story doesn't end here. Because the jet doesn't just fire and disappear. The energy it deposited doesn't just vanish. The shocked gas doesn't just cool and go back to normal. What follows the initial burst is a long, slow aftermath that can last for weeks, months, and even years. An aftermath that tells us even more about what a gamma ray burst does to the space around it. The afterglow, the expanding shock, the cocoon spreading sideways. All of these continue the story of destruction and transformation long after the initial gamma rays have faded. And that's where we're going next. The initial flash is over. The gamma rays that made the burst famous, that brief pulse of the most energetic light in the universe, lasted maybe 10 seconds, maybe 30, maybe a couple of minutes for the longest events. And then it stopped. The central engine shut down. The accretion disk drained. The black hole at the heart of the explosion went quiet. If you were an astronomer watching from a safe distance, you might think the event was finished. The burst happened. It's done. Time to move on. But the event is far from finished. In many ways, it's just getting started. Because the jet didn't simply fire a pulse of gamma rays and disappear. It deposited an almost unimaginable amount of energy into the surrounding environment. That energy is now stored in the form of a rapidly expanding shock front, a cocoon of superheated plasma, and trillions upon trillions of accelerated particles racing outward at nearly the speed of light. All of that energy has to go somewhere. And as it dissipates, as it spreads and cools and interacts with the surrounding universe over weeks and months and years, it produces a cascade of effects that tell us more about what a gamma ray burst does to space than the initial flash ever could. This is the afterglow phase, and it's one of the most revealing phenomena in all of astrophysics. Let's start with what's happening physically. At the moment, the central engine shuts off, the jet stops being fed. No more energy is being pumped into it from the accretion disk. But the jet material that was already launched is still moving. It's still plowing into the interstellar medium at relativistic speeds. The shock front at the leading edge of the jet is still advancing, still sweeping up gas, still compressing and heating everything it encounters. The shock doesn't care that the engine is turned off. It has its own momentum, its own energy. It will continue expanding until that energy is exhausted. In the minutes and hours after the burst, the shock front is still highly relativistic. It's moving at perhaps 99% of the speed of light, slightly slower than during the burst itself because it has already swept up some material and begun to decelerate. But it's still extraordinarily fast. And it's still producing intense radiation. Here's what's happening at the shock front in detail. The expanding shell of shock material has two distinct regions. There's a forward shock, which is the boundary where the jet material slams into fresh interstellar gas. And there's a reverse shock, which forms at the boundary between the jet material and the already shocked gas behind the forward shock. Both of these shocks are important, and they produce radiation with different characteristics. The forward shock is where most of the long-term afterglow emission comes from. As it sweeps up interstellar gas, it compresses and heats that gas to enormous temperatures. Electrons in the shocked gas spiral around magnetic field lines and emit synchrotron radiation. In the early afterglow, when the shock is still highly relativistic, this synchrotron emission peaks in the X-ray band. The shocked gas is so hot, and the electrons are so energetic that the radiation they produce is primarily X-rays. This is exactly what astronomers observe. Within minutes of a gamma ray burst, X-ray telescopes detect a bright afterglow at the burst's position. The Neil Gehrels Swift Observatory, launched in 2004, was specifically designed to catch these early X-ray afterglows. Swift can detect a gamma ray burst, determine its position on the sky, and swing its X-ray telescope to observe the afterglow within about 1 minute. This rapid response has been crucial for studying the early stages of afterglow evolution. As hours pass, the shock front decelerates further. It sweeps up more gas. The electrons behind the shock lose energy through radiation. The peak of the synchrotron emission shifts to lower energies. X-rays give way to ultraviolet light. Ultraviolet gives way to visible light. The afterglow becomes optically visible, sometimes bright enough to be seen with modest telescopes from Earth, even though the burst occurred billions of light years away. Think about that for a moment. An explosion so distant that its light has been traveling for billions of years, longer than our entire solar system has existed, and the afterglow is bright enough to see with a backyard telescope. That's how much energy is involved. Over the following days and weeks, the afterglow continues to fade and shift to longer wavelengths. Visible light fades to infrared. Infrared fades to radio waves. The radio afterglow can persist for months or even years after the initial burst, providing a long-lasting observable signature that allows astronomers to study the event long after the gamma rays have disappeared. This gradual dimming and reddening of the afterglow follows a remarkably predictable pattern. In most cases, the brightness at any given wavelength decreases as a power law in time. This means if you plot the brightness on a logarithmic scale against time on a logarithmic scale, you get a roughly straight line. The slope of this line tells you about the physics of the shock. How much energy was in the jet? How dense the surrounding medium is, how the magnetic field is distributed, how the electrons are being accelerated. Astronomers have developed detailed models that can fit the observed afterglow light curves and extract these physical parameters with remarkable precision. But the afterglow isn't always smooth and predictable. Sometimes there are bumps, breaks, and flares in the light curve. These irregularities tell us about additional physics happening in the system. A bump might indicate that the shock has encountered a denser region of gas, perhaps a shell of material that the star expelled before it died. A break in the light curve might signal that the jet has decelerated to the point where its beaming cone has widened beyond the observer's line of sight, causing the apparent brightness to drop more steeply. A flare might indicate late-time activity from the central engine, perhaps a final gasp of accretion onto the black hole, sending a fresh pulse of energy into the jet. One of the most interesting features in gamma-ray burst afterglows is something called a jet break. Remember how the jet is narrow, covering only a small fraction of the sky. In the early afterglow, when the shock is still highly relativistic, relativistic beaming concentrates the emission into a narrow cone. The observer only sees radiation from a small portion of the shock front, the part that's moving almost directly toward them. As the shock decelerates, the beaming cone widens. Eventually, the observer begins to see emission from a wider and wider portion of the shock. At some point, the beaming cone becomes wider than the physical extent of the jet itself. When this happens, the observer notices that the afterglow starts fading faster than before. This is the jet break. It shows up as a steepening in the afterglow light curve, a change in the slope of the power law decay. Jet breaks are important because they allow astronomers to measure the opening angle of the jet. By determining when the jet break occurs, astronomers can calculate how wide the jet was. This in turn allows them to calculate the true energy of the burst, corrected for the fact that the energy was concentrated into a narrow beam rather than spread uniformly. Most gamma-ray burst jets have opening angles between 2 and 20 degrees, with typical values around 5 to 10 degrees. These measurements confirm that gamma-ray bursts are indeed focused events, not spherical explosions. Now, let's talk about the reverse shock in more detail, because it produces some of the most dramatic early afterglow features. The reverse shock forms when the jet material, which is moving at nearly the speed of light, encounters material that has already been decelerated by the forward shock. The jet material is still moving faster than the already shocked gas, so a shock forms at the boundary between them. The reverse shock heats the jet material itself, which has a very different composition and density from the interstellar gas. Because the jet material is different from the swept-up interstellar gas, the reverse shock produces radiation with different characteristics. In some bursts, the reverse shock produces a bright optical flash in the first minutes after the burst. This flash can be extraordinarily bright. GRB 990123, observed in January of 1999, had a reverse shock optical flash that reached a visual magnitude of about 9. That's bright enough to see with a pair of binoculars, from a source that was 9 billion light years away. For a few seconds, a dying star in a galaxy 9 billion light years distant was bright enough that anyone on Earth with binoculars pointed in the right direction could have seen it. That single fact tells you more about the power of a gamma ray burst than any number could. The reverse shock is short-lived compared to the forward shock. It passes through the jet material relatively quickly and then dissipates. The forward shock, on the other hand, continues expanding for much longer, gradually sweeping up interstellar gas and producing the long-lasting afterglow that can persist for months in radio wavelengths. Let's follow the expanding shock front further outward, because its interaction with the broader interstellar environment produces effects that last far longer than the afterglow itself. As the shock expands, it sweeps up more and more gas. The total mass of swept-up gas increases with the cube of the radius. As more mass accumulates, the shock decelerates further. Eventually, perhaps months or years after the burst, the shock transitions from relativistic to non-relativistic. It slows below the speed of light and becomes an ordinary, though still extremely powerful, blast wave. At this stage, the shock behaves similarly to a supernova remnant, but with some important differences. The energy involved is comparable to or somewhat larger than a supernova. The geometry is different because of the jet structure, and the initial conditions are different because the shock started at relativistic speeds rather than the 10,000 kilometers per second, typical of supernova remnants. The blast wave continues expanding for centuries, millennia, and eventually tens of thousands of years. As it expands, it sweeps up interstellar gas and creates a bubble of hot, low-density plasma surrounded by a shell of compressed gas. This bubble can eventually grow to be several light years across, perhaps even tens of light years for the most energetic events. Inside the bubble, the temperature remains high, millions of degrees, for thousands of years. The shell of compressed gas at the boundary of the bubble is important for the wider galactic environment. When this shell encounters molecular clouds, dense regions of gas where new stars are forming, it can compress those clouds further. This compression can trigger gravitational collapse within the clouds, potentially igniting the formation of new stars. In this way, a gamma ray burst, despite being a destructive event, can actually stimulate star formation in the surrounding region. Destruction and creation are linked, but the shell can also disrupt star formation. If the shock is powerful enough, it can shred molecular clouds rather than compress them, dispersing the gas and preventing new stars from forming. Whether the effect is constructive or destructive depends on the energy of the blast wave and the density and structure of the clouds it encounters. In many cases, The answer is both. Some clouds are compressed and triggered into forming stars, while others are disrupted and dispersed. The net effect on the surrounding environment depends on the specific circumstances of each event. Now let's return to the cocoon, because this structure plays a crucial role in how a gamma ray burst affects the space around it in directions away from the jet axis. Remember from our earlier discussion that as the jet drills through the dying star, it pushes stellar material sideways, creating a hot, pressurized cocoon surrounding the jet channel. This cocoon doesn't just exist inside the star. When the jet breaks through the stellar surface, the cocoon breaks out too. The cocoon emerges from the star as a roughly spherical or ellipsoidal cloud of hot gas expanding outward at mildly relativistic speeds. Not as fast as the jet, which is moving at 99.99% of the speed of light, but still impressively fast. The cocoon material might be moving at 10 to 50% of the speed of light. That's still tens of thousands of kilometers per second, far faster than any supernova ejector. The cocoon expands outward in all directions, not just along the jet axis. This means the cocoon produces effects that are visible from any viewing angle, not just from the direction of the jet. An observer looking at the burst from the side, perpendicular to the jet, wouldn't see the intense gamma ray emission from the beam, but they would see emission from the expanding cocoon. The cocoon emission has a different character from the jet emission. It peaks at lower energies, typically in the ultraviolet or soft X-ray range, rather than in hard gamma rays. It lasts longer than the prompt gamma ray emission because the cocoon is larger and more diffuse. And it carries information about the burst's total energy and the properties of the stellar material that was shocked during the jet's passage through the star. In 2017, when astronomers detected the neutron star merger event GW170817, they observed a fascinating phenomenon related to the cocoon. The gamma ray burst associated with this merger was unusually weak, and it appeared to be viewed from a significant angle off the jet axis. In the weeks and months following the merger, the afterglow brightened rather than fading. This was interpreted as emission from a structured jet and cocoon system. As the jet and cocoon decelerated, material that was initially beamed away from us gradually became visible as the beaming cone widened. This provided direct observational evidence for the cocoon structure and confirmed that gamma ray bursts produce significant effects outside the narrow jet cone. This observation was groundbreaking because it showed that even when you're not in the direct path of the jet, the cocoon and the wider outflow still carry substantial energy. The cocoon spreads that energy over a much larger solid angle, so the intensity at any given point is lower than in the jet. But the total energy in the cocoon can be comparable to the energy in the jet itself. The cocoon ensures that a gamma ray burst affects its environment in all directions, not just along the beam axis. The effects are strongest along the jet, certainly, but they're not zero elsewhere. Let's talk about what the expanding blast wave does to the magnetic field structure of the surrounding interstellar medium. This is an aspect that gets overlooked in most popular discussions of gamma ray bursts, but it's significant for understanding the long-term impact. The interstellar medium has a weak magnetic field, typically a few microgauss. This field is organized on scales of tens or hundreds of light years, threaded through the gas in patterns shaped by the galaxy's rotation and the turbulence of previous stellar winds and supernova explosions. It's a delicate structure, built up over millions of years of galactic evolution. When a gamma-ray burst blast wave sweeps through this medium, it compresses and amplifies the magnetic field. Behind the shock front, the field can be amplified by factors of hundreds or thousands. More importantly, the shock disrupts the large-scale organization of the field. The orderly field lines that existed before the burst are tangled and randomized by the turbulence associated with the shock. The result is a region of space where the magnetic field is stronger than the surrounding medium, but chaotically organized. This matters because interstellar magnetic fields influence many astrophysical processes. They affect how gas moves through the galaxy. They influence the rate and efficiency of star formation. They guide the propagation of cosmic rays. They shape the structure of molecular clouds. When a gamma-ray burst disrupts the magnetic field in a region of space, all of these processes are affected. The gas in that region behaves differently than it did before. Star formation might proceed at a different rate. Cosmic rays might propagate along different paths. The long-term evolution of that region of the galaxy is subtly but permanently altered. Now, about cosmic rays. The shock waves associated with gamma-ray bursts are among the most efficient particle accelerators in the universe. Through a process called Fermi acceleration, charged particles are bounced back and forth across the shock front, gaining energy with each crossing. The most energetic cosmic rays, particles with energies exceeding 10 to the power of 18 electron volts, might originate from gamma-ray burst shocks. These cosmic rays don't stay near the burst. They stream outward at close to the speed of light, diffusing through the galaxy's magnetic field. Over time, they spread across the entire galaxy, contributing to the overall cosmic ray background. Every galaxy that has experienced gamma-ray bursts carries a cosmic ray signature from those events, a population of ultra-high energy particles that permeate the galactic volume and interact with gas, dust, and magnetic fields throughout the galaxy. Cosmic rays from gamma-ray bursts can ionize gas deep inside of molecular clouds, where ultraviolet and visible light from stars can't penetrate. This ionization affects the chemistry inside these clouds, altering the rates of chemical reactions and the types of molecules that form. Some of the complex organic molecules found in molecular clouds, molecules that might be important for the eventual origin of life, are produced through chemical pathways that require cosmic ray ionization. In this indirect way, gamma-ray bursts might contribute to the chemical complexity of the galaxy and even to the conditions necessary for life, even though their direct effects are overwhelmingly destructive. Let's also consider what happens to any nearby stellar systems that aren't directly in the jet's path, but are close enough to feel the effects of the expanding blast wave and the cocoon. A star system within a few tens of light years of a gamma-ray burst, but off to the side of the jet, would experience several things. First, it would receive a brief pulse of radiation. Not the full fury of the jet, but the emission from the cocoon, and the off-axis glow of the afterglow. This radiation would be primarily in the X-ray and ultraviolet range. For a burst within a few dozen light years, this off-axis radiation could still be significant, potentially hundreds or thousands of times more intense than normal background levels. For a planet with an atmosphere, this pulse of X-ray and ultraviolet radiation would cause some atmospheric chemistry changes, though far less severe than what a planet in the jet's direct path would experience. Second, the expanding blast wave would eventually reach the stellar system, though it would take years to centuries depending on the distance. By the time it arrives, the blast wave has decelerated to non-relativistic speeds, perhaps a few percent of the speed of light or less. It would wash over the stellar system, depositing heat and turbulent energy in the interstellar gas surrounding the system. The blast wave would not directly affect the star or its planets. The energy density would be far too low by this point. But it would alter the local interstellar environment, changing the density and temperature of the gas surrounding the system, and potentially affecting the system's interaction with its local medium. Third, the enhanced cosmic ray flux from the burst would arrive over a period of years to decades, depending on the distance and the structure of the intervening magnetic field. These cosmic rays would slightly increase the radiation dose received by anything in the system, including planets. For most systems, this increase would be minor and temporary. But for systems very close to the burst, the enhanced cosmic ray flux could be significant enough to affect atmospheric chemistry or biological systems. Now, let me address something important about timescales, because this is where the afterglow phase really distinguishes itself from the initial burst. The prompt gamma ray emission lasts seconds to minutes. That's the dramatic part. That's what makes headlines. But the afterglow, the decelerating shock, the expanding cocoon, and the spreading cosmic rays, these processes operate on timescales of weeks, months, years, and even millennia. The X-ray afterglow can persist for days to weeks. The optical afterglow can be observed for days to months. The radio afterglow, as I mentioned earlier, can last for months to years. Some radio afterglows have been observed more than a decade after the initial burst, and the non-relativistic blast wave, the remnant of the shock long after it has slowed to ordinary speeds, continues expanding for thousands of years, gradually merging with the general turbulence of the interstellar medium. This means the environmental effects of a gamma ray burst play out over an enormous range of timescales. The initial gamma ray pulse delivers a catastrophic dose of radiation in seconds. The afterglow radiation continues depositing energy for days to months. The blast wave sweeps through the local environment over years to millennia. The cosmic rays permeate the galaxy over millions of years. And the altered magnetic field structure and ionization state of the affected region persist for even longer, gradually being erased by the galaxy's own turbulent processes over millions to tens of millions of years. Each of these timescales affects different types of objects differently. A planet's atmosphere responds to the initial gamma ray pulse within hours, but its ozone layer might take years to recover from the enhanced ultraviolet exposure. The surrounding interstellar gas might take millennia to return to its pre-burst state. And the cosmic ray background of the galaxy carries the signature of every gamma ray burst that has ever occurred. A cumulative record of violence written in high-energy particles. Let me close with something that I find genuinely remarkable about the afterglow. It was the discovery of afterglows in 1997 that finally allowed astronomers to determine where gamma ray bursts were coming from. Before that, for 30 years after the first detection in 1967, gamma ray bursts were one of the deepest mysteries in astrophysics. The gamma rays arrived, lasted a few seconds, and vanished. There was nothing left to study. No way to determine the distance. No way to figure out what caused them. The breakthrough came when the Italian-Dutch satellite BeppoSAX detected the X-ray afterglow of GRB 970228 in February of 1997. Within hours, ground-based telescopes found the optical afterglow. And for the first time, astronomers could precisely locate a gamma ray burst on the sky and identify its host galaxy. The afterglow gave them a target. They could measure the redshift of the host galaxy and determine the distance. The result was stunning. The burst was billions of light years away, confirming that gamma ray bursts were the most energetic events in the universe. Without the afterglow, we might still be in the dark about what gamma ray bursts are. The prompt gamma ray emission tells us that something extreme happened, but the afterglow tells us where it happened, how much energy was involved, what the surrounding environment looked like, and what physical processes were at work. The afterglow is the forensic evidence left at the scene of the most violent crime the universe can commit. It lets us watch in real time as a relativistic explosion decelerates, spreads, and eventually merges with the ordinary turbulence of the interstellar medium. It connects a brief flash of gamma rays to a months-long process of energy dissipation and environmental transformation. The afterglow is not just an epilogue, it is the main story. The gamma ray burst might be the headline, the thing that grabs your attention, but the afterglow is the book. The detailed narrative of what happens when the most concentrated beam of energy in the universe collides with the material between the stars, deposits its energy over light years of space, and slowly, gradually, over weeks and months and years and centuries, transforms its surroundings in ways that persist long after the last photon has faded. The burst is finished. The afterglow is fading. The blast wave is expanding into the dark between the stars. But the story isn't over yet, because we haven't yet talked about what all of this means for worlds, for planets, for atmospheres, oceans, and anything alive that might be unfortunate enough to exist in the wrong place at the wrong time. The physics of shock waves and synchrotron radiation and magnetic field amplification is fascinating. But the question that matters most to us, the question that connects gamma ray bursts to our own existence, is simpler and more personal. What happens to a world caught in the beam? That's where we're going next. Everything we've explored so far, the jet formation, the relativistic shocks, the afterglow, the expanding blast wave, all of it has been about what a gamma ray burst does to gas and dust and magnetic fields, to the raw material of space. But now we need to ask the question that really matters. What does a gamma ray burst do to a world? Not a cloud of interstellar hydrogen, not a diffused nebula, a world, a planet with an atmosphere, with oceans, maybe with life. What happens when the beam finds something like Earth? Let's set the scene carefully, because the answer depends entirely on the details. How far away is the burst? How energetic is it? Is the planet directly in the jet's path or slightly off axis? Does the planet have a magnetic field? How thick is its atmosphere? What kind of star does it orbit? All of these factors determine whether a gamma ray burst is a minor inconvenience, a serious problem, or an extinction-level catastrophe. Let's start with the worst case. A planet directly in the path of a powerful, long gamma ray burst at a distance of about 100 light years. 100 light years is close by galactic standards, but still an enormous distance by human standards. It's roughly 25 times farther than the nearest star to our sun. There are thousands of star systems within 100 light years of Earth. So this isn't an absurdly close distance. It's a plausible distance. At 100 light years, a planet in the direct path of the jet receives an extraordinary dose of gamma ray radiation. The energy flux arriving at the planet would be roughly equivalent to 10,000 times the normal energy output of the planet's own star, concentrated into a burst lasting seconds to minutes. Let me say that differently. For those few seconds, the gamma ray burst delivers more energy per square meter to the planet's surface than 10,000 suns would. Now, gamma rays don't interact with matter the same way visible light does. Visible light from a star is mostly absorbed or reflected by a planet's atmosphere and surface. It warms the planet, it drives weather, it powers photosynthesis. Gamma rays are different. They're far more energetic. They penetrate deeper into the atmosphere. And when they interact with atmospheric molecules, they don't just warm them, they shatter them. The first thing the gamma rays do is slam into the upper atmosphere. Nitrogen and oxygen molecules, which make up the bulk of an Earth-like atmosphere, absorb the gamma ray photons. But the photons carry so much energy that instead of gently exciting the molecules, they blast them apart. Nitrogen molecules are broken into individual nitrogen atoms. Oxygen molecules are broken into individual oxygen atoms. These highly reactive atoms then recombine in new configurations. And this is where the real damage begins. When individual nitrogen and oxygen atoms are liberated in the upper atmosphere, they combine to form nitrogen oxides, nitric oxide and nitrogen dioxide primarily. These molecules are chemically aggressive. They're catalysts for a specific chemical reaction that is devastatingly relevant for life. They destroy ozone. Ozone is a molecule made of 3 oxygen atoms. It exists in a thin layer in the upper atmosphere, roughly 15 to 35 kilometers above the surface in Earth's case. This layer is almost vanishingly thin. If you compressed all the ozone in Earth's atmosphere into a single layer at sea level pressure, it would be only about 3 millimeters thick. 3 millimeters. That's thinner than 2 stacked coins. And yet this gossamer thin layer is one of the most important shields life has ever had. Ozone absorbs ultraviolet radiation from the sun. Specifically, it absorbs UVB and UVC radiation, the most biologically damaging wavelengths. Without the ozone layer, this ultraviolet radiation would reach the planet's surface at full intensity. UVB radiation damages DNA. It causes mutations. It kills single-celled organisms. It damages the photosynthetic machinery in plants and phytoplankton. It causes skin cancer and cataracts in animals. A UVC radiation is even more dangerous, but is currently blocked almost entirely by ozone. Without ozone protection, the surface of a planet becomes a much more hostile place for life. The nitrogen oxides produced by a gamma ray burst attack the ozone layer through a catalytic cycle. A single nitrogen oxide molecule can destroy thousands of ozone molecules before it's eventually removed from the atmosphere. The gamma ray burst doesn't need to directly destroy the ozone. It just needs to produce enough nitrogen oxides to trigger a chain reaction that does the job over weeks and months. For a powerful burst at 100 light years, the models are stark. Computer simulations conducted by researchers at NASA and several universities have shown that such a burst could destroy anywhere from 30 to 90% of a planet's ozone layer. Depending on the specifics of the burst energy, the planet's atmospheric composition, and whether the burst hits the planet's day side or night side, losing 30% of the ozone layer would be bad. Ultraviolet radiation reaching the surface would increase significantly. Sensitive organisms would suffer. Ecosystems that depend on UV-sensitive species would be stressed. But life would survive. It would adapt. It would recover over the years as the ozone layer gradually rebuilt itself. Losing 90% of the ozone layer would be catastrophic. The surface ultraviolet flux would increase by a factor of 10 or more. The UVB radiation reaching the ground would be intense enough to cause severe DNA damage in exposed organisms within hours. Phytoplankton, the microscopic organisms that form the base of the marine food chain and produce a significant fraction of Earth's oxygen, would be devastated. Phytoplankton live in the upper layers of the ocean where sunlight penetrates. They can't hide from ultraviolet radiation. A massive increase in UVB would kill them in enormous numbers, collapsing marine food webs from the bottom up. Land plants would also suffer. Their leaves would experience UV damage, reducing their ability to photosynthesize. Crops would fail. Forests would thin. The entire terrestrial biosphere would be stressed simultaneously. Animals exposed to direct sunlight would develop severe UV damage. Amphibians, whose eggs are particularly sensitive to ultraviolet radiation, would be hit especially hard. But the damage doesn't stop with ozone depletion. The nitrogen oxides produced in the upper atmosphere also form nitrogen dioxide, which is a brown gas that absorbs visible light. Large quantities of nitrogen dioxide in the atmosphere would create a visible haze, dimming the sunlight reaching the surface. This is sometimes called a cosmic winter or an ultraviolet spring, a grim combination of reduced visible light and increased ultraviolet light. Less visible light means less photosynthesis and cooler surface temperatures. More ultraviolet light means more biological damage. The planet gets hit from both directions simultaneously. It's darker and colder, which stresses ecosystems adapted to normal light levels and temperatures. And it's more irradiated with ultraviolet, which directly damages the organisms trying to survive those stressed conditions. The nitrogen oxides also combine with water vapor to form nitric acid, which falls as acid rain. This acid rain would lower the pH of surface waters, lakes, streams, and shallow ocean environments. Organisms that are sensitive to pH changes, including many shellfish, corals, and plankton species, would be affected. The acid rain wouldn't be as extreme as, say, the aftermath of a massive volcanic eruption, but it would add another stress on top of all the others. Now, how long would all of this last? The ozone depletion caused by a gamma ray burst wouldn't be permanent. The nitrogen oxides are eventually removed from the atmosphere through natural chemical processes. Sunlight itself breaks down nitrogen dioxide over time. Rain washes nitric acid out of the atmosphere. Gradually, over a period of years to perhaps a decade, the ozone layer would rebuild. The atmosphere would return to something close to its normal state, but a decade is a long time for a biosphere under severe stress. 10 years of elevated ultraviolet radiation, reduced visible light, and acid deposition could be enough to push vulnerable species over the edge into extinction. Species that were already stressed, that had small populations, that depended on UV-sensitive food sources, or that couldn't shelter from the increased radiation, would be most at risk. The result wouldn't necessarily be a sudden mass die-off. It would be more like a slow squeeze, year after year of degraded conditions, gradually eroding populations, until some species simply can't hold on any longer. This brings us to one of the most intriguing hypotheses in paleontology. The idea that a gamma-ray burst might have caused or contributed to a real mass extinction on Earth. About 445 million years ago, at the end of the Ordovician period, Earth experienced one of the 5 great mass extinctions in its history. Approximately 85% of all marine species went extinct. This was a catastrophic event for life on Earth, second only to the Great Permian extinction in terms of the percentage of species lost. The Ordovician extinction happened in two pulses, separated by about 1 million years, which has puzzled paleontologists for decades. The traditional explanation involves glaciation. During the late Ordovician, the supercontinent Gondwana drifted over the South Pole, and massive ice sheets formed. Sea levels dropped dramatically, destroying the shallow marine habitats where most Ordovician life lived. Then, when the glaciers retreated, sea levels rose again, but ocean chemistry had changed. Oxygen levels in the deep ocean had dropped, creating anoxic conditions that killed many of the organisms that survived the initial cooling. This glaciation model explains a lot, but it has gaps. The cooling seems to have been more severe and more sudden than the slow drift of a continent would typically produce. Some researchers have pointed out that the two-pulse structure of the extinction, with an initial kill followed by a second kill about 1 million years later, is hard to explain with glaciation alone. In 2004, astrophysicists Adrian Melott and Brian Thomas proposed that a gamma-ray burst could have triggered or amplified the Ordovician extinction. Their argument went like this: a gamma-ray burst within a few thousand light-years of Earth could have depleted the ozone layer severely. The increased ultraviolet radiation would have killed phytoplankton and other surface-dwelling marine organisms, collapsing marine food webs. The nitrogen dioxide haze would have cooled the planet, potentially triggering or enhancing glaciation. The acid rain would have further stressed marine ecosystems. All of these effects together could explain the first pulse of extinction. The second pulse, 1 million years later, could be explained by the delayed effects of glaciation and ocean chemistry changes set in motion by the initial burst. This hypothesis is not proven. It's important to be clear about that. We have no direct evidence that a gamma-ray burst hit Earth 445 million years ago. There's no smoking gun, no chemical signature in the rock record that says definitively that a burst occurred. The hypothesis remains speculative, but it's scientifically plausible. The physics works, the timing is consistent, and the pattern of extinction, particularly the severity and the sudden onset, is consistent with what models predict a nearby gamma-ray burst would produce. What makes this hypothesis particularly interesting is that it doesn't require anything unusual. Gamma-ray bursts happen. They've been happening throughout the history of the universe. The Milky Way has experienced them. The rate of long gamma-ray bursts in a galaxy like the Milky Way is estimated at somewhere between 1 every 100,000 years and 1 every million years. Over the 4.5 billion year history of Earth, there have probably been several thousand gamma-ray bursts in our galaxy. Most of them were far away and their jets were pointed in other directions. But statistically, over billions of years, it's likely that at least 1 or 2 have been close enough and aimed in the right direction to significantly affect Earth's atmosphere. Now, let's step back and ask a broader question. How close does a gamma-ray burst need to be to cause serious damage to a planet like Earth? The answer depends on what you mean by serious damage. For a powerful long gamma-ray burst with a total isotropic equivalent energy of about 10 to the power of 46 joules, which is toward the upper end of observed bursts. The danger zone for significant ozone depletion, meaning a loss of 30% or more, extends to roughly 3,000 to 6,000 light years if the planet is directly in the jet's path. That's a substantial fraction of the distance between our Sun and the center of the Milky Way. Within that range, any planet unlucky enough to be in the beam's direct path would suffer meaningful atmospheric damage. For less energetic bursts, the danger zone shrinks. A typical long gamma-ray burst might pose a serious threat out to a few hundred light-years. A short gamma-ray burst from a neutron star merger, which is generally less energetic than a long burst, might be dangerous out to a few tens of light-years. But remember the directionality. The jet covers only a tiny fraction of the sky. The chance that any particular planet lies in the jet's path is small. Even if a gamma-ray burst occurs relatively nearby, say within 1,000 light-years, the odds of the jet being aimed at Earth are probably less than 1 in 1,000. The combination of rarity and directionality means that the overall probability of a gamma-ray burst affecting Earth in any given century or millennium is extremely low. The best estimates suggest that Earth experiences a biologically significant gamma-ray burst perhaps once every few 100 million years on average. This is worth emphasizing because it brings important perspective. Gamma-ray bursts are the most violent events in the universe. Their effects on anything in their path are catastrophic, but they're also rare, and their beams are narrow. The universe is not a shooting gallery where planets are constantly being zapped by gamma-ray bursts. It's more like a vast dark room with occasional laser beams flashing through it at random angles. If you're in the path, it's devastating. But the room is so large and the beams so narrow that the chance of being hit at any given moment is vanishingly small. Now, let's clearly distinguish gamma-ray bursts from ordinary supernovae, because the two events are often confused, and the distinction matters enormously for understanding their effects on surrounding space. A supernova is a powerful explosion, absolutely. When a massive star explodes as a supernova, it releases roughly 10 to the power of 46 joules of total energy. That's actually more total energy than a gamma-ray burst. But here's the crucial difference. About 99% of a supernova's energy is carried away by neutrinos. Neutrinos barely interact with matter. They pass through entire planets without noticing. They're irrelevant for the purposes of environmental damage. The remaining 1% of the supernova's energy goes into the kinetic energy of the expanding shell of debris and into electromagnetic radiation. The electromagnetic energy is roughly 10 to the power of 43 joules, spread evenly in all directions. A gamma-ray burst, by contrast, concentrates roughly 10 to the power of 44 joules of electromagnetic energy into a beam covering perhaps 1,000th of the sky. Within that beam, the energy per unit area is about 10,000 times higher than what a supernova delivers at the same distance. This means a supernova has to be much closer to cause the same level of damage. A supernova would need to be within about 30 to 50 light years of Earth to significantly deplete the ozone layer. At that distance, the ultraviolet flash and the cosmic rays from the expanding remnant would produce enough nitrogen oxides to seriously damage atmospheric ozone. A gamma-ray burst, because of its focused beam, can cause the same damage from thousands of light years away. The beam concentrates the energy so effectively that it extends the danger zone by a factor of roughly 100 compared to a supernova with similar total electromagnetic output. There's another important difference: the time scale. A supernova's energy arrives gradually. The initial flash of light takes a few weeks to peak and then fades over months. The cosmic rays arrive over thousands of years as the remnant expands and accelerates particles. The total energy deposit is spread over long time scales, giving a planet's atmosphere time to respond and partially recover between doses. A gamma-ray burst delivers its energy in seconds. The entire gamma-ray pulse, carrying an enormous dose of radiation, arrives essentially instantaneously. There's no warning, no gradual build-up. 1 second the sky is normal. The next second, a wall of gamma rays arrives. The atmosphere has no time to respond, no time to adjust. The nitrogen oxides are produced in a sudden pulse, and the ozone destruction begins immediately. This sudden delivery is actually worse for a biosphere than the same total energy delivered gradually. A planet can adapt to slowly changing conditions. Organisms can migrate, change behavior, or evolve in response to gradual environmental shifts. But a sudden, overwhelming pulse of radiation leaves no time for adaptation. The damage is done before any biological response is possible. There's also the matter of what comes after the initial pulse. A supernova near Earth would produce a long-lived supernova remnant, an expanding bubble of hot gas and cosmic rays that would interact with the solar system for thousands of years. This long-term exposure would maintain elevated cosmic ray levels and possibly continue to stress the ozone layer for extended periods. A gamma-ray burst produces a similar expanding remnant, but because the burst might be much farther away, the remnant might never reach the affected planet. The gamma rays and the prompt ultraviolet flash travel at the speed of light and arrive first. The physical blast wave, moving at initially relativistic but rapidly decelerating speeds, might take centuries or millennia to reach a planet hundreds of light years away. And by the time it arrives, it might have dissipated to the point where it's no longer significant. For a distant gamma-ray burst, the damage is done entirely by the electromagnetic pulse. The physical remnant never arrives. This makes gamma-ray bursts a particularly insidious threat. They reach out across thousands of light years with a beam of radiation that travels at the speed of light. There's no advance warning. You can't see it coming. The first sign that anything is wrong is the arrival of the gamma rays themselves. By the time you know it's happening, the damage is already being done. For a civilization with advanced astronomical instruments, there might be some warning in theory. If they detected a massive star near the end of its life in the right part of the sky, or they detected gravitational waves from an impending neutron star merger, they might have hours or days of warning. But for a biosphere without technology, for the organisms that lived on Earth 445 million years ago, there would be no warning at all. The sky would simply change one day. The ozone layer would begin to thin. The ultraviolet radiation would increase, and the slow catastrophe would unfold over years, while the organisms had no idea what had happened or why their world was suddenly becoming more hostile. Let's end by putting all of this into perspective, because despite everything I've described, despite the incredible violence and the genuine danger, gamma ray bursts are not something you need to worry about on a personal level. The probability of a gamma ray burst affecting Earth in any given year is extraordinarily low. The best estimates suggest something like 1 chance in several hundred million per year. You are incomparably more likely to be struck by lightning, win a major lottery, or be hit by a falling meteorite than you are to be affected by a gamma ray burst in your lifetime. The odds are so low that it's not a meaningful risk for any individual or even any civilization to worry about on timescales shorter than millions of years. Moreover, the rate of gamma ray bursts in the Milky Way has been declining over cosmic time. Gamma ray bursts are more common in galaxies with low metallicity, meaning galaxies where the stars contain fewer heavy elements. In the early universe, when stars were made primarily of hydrogen and helium, gamma ray bursts were more frequent. As successive generations of stars enriched the galaxy with heavy elements, the conditions for producing gamma ray bursts became less common. The Milky Way today, with its relatively high metallicity, probably produces fewer gamma ray bursts than it did billions of years ago. The danger, such as it is, was greater in the past than it is now. There's also the simple geometry of it. Even when a gamma ray burst does occur in the Milky Way, the jet is aimed in a random direction. The probability that it's aimed at any particular star system is tiny. The jet covers maybe 1/1000th of the sky. The galaxy contains hundreds of billions of star systems. For any given burst, the chance that the jet is aimed at Earth specifically is roughly 1 in 100 billion. Combine that with the low rate of bursts in the galaxy, and the risk becomes negligible on any timescale relevant to human civilization. But on geological timescales, over hundreds of millions or billions of years, the probability becomes significant. Over the 4.5 billion year history of Earth, it is statistically likely that our planet has been affected by at least one gamma ray burst. The geological record is long, and the evidence for a gamma ray burst would be subtle, a temporary change in atmospheric chemistry, a pattern of extinction that's hard to explain by other means. What a gamma ray burst does to space around it is, in the end, a story about concentration. The universe is full of energy. Stars produce enormous amounts of it. Supernovae release staggering quantities in single events. But gamma ray bursts take that energy and focus it. They compress it in time, delivering billions of years worth of stellar energy in seconds. They compress it in space, channeling it into a beam narrower than a few degrees. This double compression in time and in space is what makes them unique. It's what allows them to reach across light years and reshape everything in their path. It's what makes them capable of sterilizing planets from thousands of light years away, while leaving everything outside the beam untouched. A gamma ray burst is the universe's most precise weapon, not the most energetic in absolute terms. Supernovae release more total energy. The Big Bang released infinitely more. But in terms of energy delivered per unit area, per unit time to a target, nothing in the known universe competes with a gamma ray burst jet. It is the most concentrated expression of violence that nature has devised. And yet, that violence is rare. It's fleeting. It lasts seconds. The afterglow fades in months. The blast wave dissipates in millennia. The ozone layer recovers in decades. Given enough time, even the most devastated region of space returns to something like normal. New molecules form. New dust condenses. New stars ignite. New planets coalesce from the debris. Life, if it survived anywhere nearby, begins the slow process of recovery and diversification. This is perhaps the most profound lesson from studying gamma ray bursts. The universe is capable of extraordinary violence. Events of almost incomprehensible power occur regularly across the cosmos. Beams of energy capable of sterilizing entire planetary systems flash through galaxies at the speed of light. And yet, the universe is also extraordinarily resilient. Life on Earth has survived for nearly 4 billion years, despite asteroid impacts, supernovae, volcanic catastrophes, ice ages, and possibly gamma ray bursts. Each time life was knocked down, each time it got back up. Each time It diversified and filled the world again with new forms, new species, new ways of being alive. The next time you look up at the night sky, remember what's out there. Somewhere in the darkness, right now, a massive star is collapsing. A jet is forming. A beam of gamma rays is punching through a dying star and erupting into space at nearly the speed of light. Somewhere, a relativistic shockwave is slamming into interstellar gas, heating it to billions of degrees. Somewhere, a planet's ozone layer is being shredded by radiation from an explosion that happened thousands of light years away. But also remember this: space is vast. The beams are narrow, and Earth, orbiting a quiet yellow star in a calm suburb of the Milky Way, is about as safe as any planet can be. We're here. We've been here for 4.5 billion years. Life has survived everything the universe has thrown at it so far. And on this particular night, on this particular planet, you're alive. You're breathing air protected by a thin layer of ozone 3 millimeters thick. You're warmed by a stable star that won't die for another 5 billion years. You're looking up at a sky full of stars that are, for the moment, perfectly peaceful. The universe is violent, but it's also, against all odds, beautiful. And you're part of it. Made of atoms forged in stars that died long ago. Living on a world that has weathered cosmic storms you can barely imagine. Looking up at the same stars that have witnessed the most powerful explosions in nature and thinking about what it all means. That's what a gamma ray burst does to space around it. It reshapes matter, rewrites chemistry, and reminds us that the cosmos operates on scales of power that dwarf anything in human experience. But it also reminds us that the universe, for all its violence, has allowed something fragile and extraordinary to exist on one small planet, in one quiet corner of one galaxy. Life, consciousness, the ability to wonder about gamma ray bursts in the first place, and perhaps that's the most remarkable thing of all. Not the violence of the burst, but the fact that something as delicate as a living mind can exist in a universe capable of producing it. Thank you for joining me on this journey. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos. And remember, the universe is wild, but you're here. And that means something extraordinary has already happened. Good night, and may the beams always miss us.